Okay, so let's go over the answers from quiz 6. Number 1, you have A is a subset of C, B is a subset of D. Prove that implies that A union B is a subset of C union B. Okay, so some common mistakes. You need to use this hypothesis. You're going to use the fact that A is a subset of C and B is a subset of D, but that's not where you start the proof. You start, really the substance of the proof, you're starting here. We want to show that A union B is a subset of C union D. So you take an arbitrary element of A union B. That's really the first major statement that I'm looking for. I mean, you can say let A be a subset of C, let B C a subset of D, but you don't even really need to do that first. What I would do, I would start with let X be an element of A union B. Now, think about, I like to give partial credit on proofs and things. If you wrote that, and then you wrote, then X is an element of C union D, and you didn't write anything else, I would give you credit, partial credit, because it proves to me you understand the technique. You take an arbitrary element of this set, and you prove until you get down to this point that X is an element of this set. That's the outline of this proof. So just by doing this, you get partial credit on the test, or even on this quiz, right? Like I think I counted this 7 points out of 20 points on the quiz. So you get 2 points for that. So basically half the technique, over half the proof. To me, you're proving. You show me that you know the technique. Okay. Now, what does it mean for X to be an element of A union B? That tells me that X is an element of A, or X is an element of B. A lot of people concluded that X is an element of A, or even started with let X be an element of A. That's not true. X doesn't have to be in A. X could be in B. So you really have to keep this statement combined. X is an element of A, or X is an element of B. You cannot conclude that X is in A. It's either in A or in B, or it could be both. Okay? So you need that statement. All right. Now, here's where we're going to use the hypothesis. We know that A is a subset of C. So I would say since A is a subset of C, X is an element of C. I cannot read it like this. If I said X is in C, that could be false. X doesn't have to be in C. Because if X was in B, then X wouldn't be in C, necessarily. So the only thing that would be correct is saying X is in C or X is in B. Do you see the subtlety there? This is a true statement. If X is in A or X is in B, then I can conclude that X is in C or X is in B. Okay? If I left off or X is in B, it's technically not correct. It's not. We don't know for sure that X is in C. But I do know for sure that X is in C or X is in B. Similarly, since B is a subset of D, I can conclude that X is an element of C or X is an element of D. Okay? You see how I did that? I went one step at a time. I kept my or statement. I can see maybe trying to do this in one line, but I'm choosing to break it up into 2 steps. I know X is in A or in B, and I conclude X is in C or B, and I can conclude X is in C or D. But what does this mean? Then X, by definition of union, X is in C union D. That's really, I'm pretty much done. If you had that much, you can conclude there. Some people might just kind of finish it off. Thus, A union B as a subset, C union D. Okay? Any questions? So for if-then statement, if the conclusion is a subset type of statement, you always start here, take an arbitrary element of this set, and you're done when you've shown that arbitrary element was here. Then you can conclude that statement about subsets. All right. Any questions? That? All right. So, we want to show that A cross B intersects C equals A cross B intersect A cross C. Now I showed you 2 or 3 ways to prove these. You could make it a 2-part proof. You could show that this is a subset of this, and then show this is a subset of this, therefore they're equal. I think it's faster to either use a chain of equal signs, start off with this set, and show that it equals another set in set builder notation, and then continue until you end up with equals this set. Another way to do it is a chain of if and only if statements. So I probably prefer, I'm going to do that way. So I'm going to take an arbitrary element of this set. I'll say x comma y is an element of A cross B intersects C. Why did I choose an ordered pair from an arbitrary element? Because the Cartesian product here, that's what, when you have a Cartesian product, then it's the only time when you use ordered pairs. So I have an arbitrary, so this point, this ordered pair, is in this set, if and only if x is an element of A and y is an element of B intersects C. These are if and only if, this is an if and only if statement that is true because I'm using the definition of the Cartesian product here. That's really what I'm using here. So this is the definition of the Cartesian product. Okay? All right. Now I'm going to use the definition of intersection. So x is an element of A, and y is an element of B, and y is an element of C. I might even put parentheses here. So this is the definition of an intersection. If y is in this intersection, then that means that y is in B and y is in C. So that justifies this if and only if statement. So I'm using the definition of intersection. Now I'm going to use it's really a distributive law. I don't really need this distributive law because these are all and statements. You don't really need parentheses when everything is the same symbol. If it's all ands. But I'm going to just break this up and I'm going to say this is the same as saying x is in A and y is in B, and x is in A and y is in C. So you can think of that as distributive law. Okay. Why would I do that? So I want to, because I know where I'm going to go. I'm trying to get something with A cross B and A cross C, and some kind of intersection. Okay. Well, here we go. So I can convert it. If x is in A and y is in B, then by the definition of the Cartesian product, I can say that x comma y is an element of A cross B. And I can say that x comma y is an element of A cross C. So I'm using the definition of Cartesian product again. Well, if this point is in this set and the same point is in this set, then it's in the intersection of these two sets. So that's the definition of intersection again. So then x comma y is an element of A cross B intersect A cross C. That's the definition of intersection. We know that definitions are if and only of statements. So I mean, I'm justified in using these if and only of statements.
Wait, why are you justified?
I'm given a reason for each one of these statements, and my reasons are definitions. And really, and there's this is distributive law. So really, an equivalence of two statements. So P and Q and R is the same as P and Q and P and R. That's the other kind of distributive law that I'm using there. But the rest of them are definitions, and definitions are if and only of statements. I mean, this means exactly this. They're interchangeable. These two statements are interchangeable. They're equivalent statements. So I can have an if and only if statement. This implies this implies that, so we use if and only if. So I have this long chain. I know that I have an element in this set means that element is in this set. Therefore, the two sets are equivalent, or equal, I mean. Thus, A cross B intersects C equals A cross B intersect A cross C. What I'm really showing, I'm doing the two-sided proof. If you read it this way, you start with an arbitrary element of here and show it lives here. But if I read it backwards, I start an arbitrary element of this set and prove that it also lives in this set. So I'm showing both. I'm showing this and this, and kind of the reverse containing. But if and only if statements do them at the same time. Okay.
Isn't there something specific that you're not that you let?
Yeah, you wouldn't want to put any words in it that would only make sense if you're reading it in one direction. Like, I would not say, let this be in here, because that implies that I'm reading it only in the forward direction. Because you could read it backwards. If I said like x is in A and y is in B intersect C, let this, and it doesn't make sense when you read it the other direction. And you wouldn't use words like then, because then implies that something came after, so you'd only be reading in one direction. So that's the thing. Usually people write a proof in the forward direction. What you could do, you could write in the forward direction, and you'd have all these, then this, then this, then this. But then you could realize at the end, well, actually, this statement implies this one. So then you could erase your thens and just replace them with if and only if statements, and you have your proof. So a lot of people did that. So a lot of people put like, let this be in here, then this, then this, then this, then this, then this. Okay, that's great, but you've only shown this direction, that this set is a subset of this one. But if you erase it, all those thens, and replace it with if and only if, if and only if, if and only if, then you show this as well, so they must be equal. Any questions about that?
Do we have to put the justification or no?
If it's obvious, I usually sometimes I don't. The problem is if you go from like this to like this, like that's not. These are not. This statement is not equivalent to this statement. Like this one, it's. I don't want you guys to jump lines in your proofs and just say, okay, well X is in here. Well, clearly it's in here. And that you're just jumping too much. It's too many steps. I would just go use one definition at a time. Like here, I'm just unraveling the definition of intersection. Here, I'm just rearranging the and statements. Here, I'm just using one definition of cross product. Using the definition of cross product. Here, I'm just using the definition of intersection. Okay. I mean, you only want you probably should think about it that way. If you had to justify it, could you just do it with one justification? You don't want to put like 5 reasons in one line. That kind of tells you probably using too much in one line. I kind of was in a bad habit. I think I said these things when I was writing these proofs. I don't think I wrote them out. But I'm fine with just if you show all the little steps, I think I'm fine with that. Any other questions? So there's 2 or 3 different correct techniques for proving 2 sets are equal. Okay? You don't have to use one, but I would recommend if you like one way, stick to it and learn how to do it well. Don't put, like, you can't put equal signs here. This is not a set. This is a statement. So this statement is true if and only if this statement is true. So watch out for that. I mean, some people put equal signs here when they really mean if and only if.
So if you're just writing paragraph notation, you could just write IFF.
Sure.
Each one of those
Yep. Yep. Any other questions? Number 3 went well. I think there was actually, some people noticed several counterexamples. So you had to show that n squared plus 17n plus 17 is not necessarily prime. Right, so the statement is, for every natural number n, this integer is prime. So to disprove this with a counterexample, you had to find a value for n that makes this quantity not prime. The easiest example probably is actually the number 1. A lot of people notice that. Like, you could let n equal 1. So once you come up with your counterexample, you have to demonstrate it as a counterexample. So how would I show that this is a counterexample? Well, I have to pick a natural number n and then show that this is not prime. Okay? So then n squared plus 17n plus 17 equals 1 squared plus 17 plus 17 is 35. And I believe 35 is not prime, but I still haven't shown that it's not prime. So I would say 35 equals, 5 times 7. Which is not prime. Okay. 17 works. Some of you guys notice that. 2 works. There's actually a lot of counterexamples for this. There's an infinite number of them.
Was it like every prime number and 0 and 1?
It was for all natural numbers. So for any natural number, it says for all natural numbers, this integer is not prime, is prime. But here's an integer or a natural number for which this quantity is not prime. Any multiple of 17 would work, because if you plug in a multiple of 17 here and a multiple of 17 here, and all 3 terms would have a factor of 17, which you could factor out. Okay. All right, any questions about that? So for counterproofs, for disproofs rather, by counterexample, you pick your counterexample, then you demonstrate that it disproves the statement. So if you claim this is prime, you'd have to pick a natural number where it's not prime. Okay. All right, so that's kind of a review of chapters 8 and 9. In chapter 9, this is all we did for chapter 9. So I know the test is on chapters 4 through 10. The only thing from chapter 9 is disproved by a counterexample. So in chapter 8, you have these 2 types of proofs where showing one set is a subset of the other, and then in these proofs where you're showing 2 sets are equal. Okay. All right. So let me go ahead and collect your homework from chapter 10. We'll go over that. You press down. It's all yours. There, please. All right. So, how'd it go?
The ones I spent most time on was 2 and 13.
Yeah. So there's a common, you in the inductive step, you gotta show the statement's true when for k plus 1. So for example, for number 2, let's look at this. So here's your kind of the right-hand side, right, of this equation. Looks like this. So you need to tell yourself, what is this going to look like for k plus 1? That's what I would do. I mean, because you got to know where you're going. So what if you replace n with k plus 1? It would look like k plus 1 times k plus 1 plus 1 times 2 times parentheses k plus 1 plus 1 all over 6. Right? If you replace n with k plus 1, that's what it should look like. So sometimes it's actually easier to start with this and go backward and like just kind of simplify this expression than it is. Did you find that when you had a lot of this stuff to get it to look exactly like this form? It can be might be kind of difficult. But if you should at least write this down before you try to prove this, because you need to know what it's going to look like at the end. Okay. What I would suggest if you get stuck, try to figure out what it looks like it's going to look like at the end, and then maybe go backwards. Like, let's simplify this a little bit. So k plus 1 plus 1, that would be k plus 2. 2 times k plus 1, the quantity k plus 1 plus 1, that would give me 2k. I have plus 2 plus 1, so it would actually look like this. So it's probably more likely that you got to this step, and then maybe you might be confused about where to go next. But this would actually be the last. You would actually get here and then go this way. So this is kind of like the scratch work, right? You got to like know where you're going, and then try to have whatever you have kind of make it look like that. Okay. So this is 10, number 2. You had 5 problems and 3 of them were odd. So I mean, you have an example of a proof for this. If you want to refer to that. So I'm going to focus on these. So the sum of the first n square numbers, perfect square numbers, will equal n times n plus 1 times 2n plus 1 all over 6. This is for integers. I'm sorry, natural numbers. Okay. Proof. We'll use induction. Basis step. So you choose the smallest n. Some of your statements where n was a natural number, some of them where n was greater than or equal to 0. So your basis step is going to be the smallest one. In this case, we're going to let n equal 1. Okay? And what does the statement say? So when n equals 1, we have 1 squared on the left side. And on the right side, it would be 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. Is that true?
Yeah.
So we get 1 on the left-hand side, and here you get 2 times 3, so 2 times 3 over 6.
6 over 6.
Yeah, 6 over 6, which is true. Okay, so the basis step is usually more like a verification that it works for the smallest n. And it should, in this case, this is a little bit more complicated than other formulas. So, all right. So it's true for n equals 1. All right. So just to kind of remind you, the steps for induction. So you show the statement is true for the smallest natural number, or smallest integer, which are 0 or 1. Okay, show it's true for 1. Then, in the inductive step, you assume it's true for some integer, some natural number k, and show that that forces it to be true for k plus 1. When you combine these two steps, then logically you can assume the statement must be true for all natural numbers. Because if it's true for 1, then this says it's true for 2. If it's true for 2, then it must be, this step shows it's true for 3. If it's true for 3, then it must be true for 4. If it's true for 4, then it must be true for 5. And then therefore, you just, like dominoes, they all knock each other down, and it must be true for all natural numbers. So you have the basis step, then you say, suppose the same is true for k. So suppose 1 squared plus 2 squared plus 3 squared up to k squared equals k times k plus 1 times 2k plus 1 all over 6 for some natural number k. Again, you know, you might get bogged down in these little details, okay? But if you're showing me the outline of the proof, I can see you know where to go next. I want to give you, you know, credit for the technique, using the technique correctly. Don't worry too much about this. And we did this when we first practiced direct proofs. Sometimes you should know what the last statement looks like. It's going to look like 1 squared plus 2 squared plus 3 squared all the way up to plus k plus 1, the quantity squared, and I just erased this. What does this look like when k equals 1 for k plus 1, when n equals k plus 1? So that should be at the end. So you can kind of work backwards too. So you can work from both ends, just like when we did when we first started direct proofs. Okay, any questions so far? Okay, so we assume this is true. If the statement is true when n equals k plus 1, then this side would end with k plus 1, the quantity squared. So what I'm going to do, I'm going to add k plus 1, the quantity squared, to both sides of this equation. And I'm going to rearrange the right-hand side. Okay, then 1 squared plus 2 squared plus 3 squared plus k squared plus k plus 1, the quantity squared, will equal this fraction plus k plus 1, the quantity squared. Okay? So I'll be done basically with this inductive step if I can show that this stuff looks like the right formula, right? I mean, it'll look like this formula replacing this with k plus 1. Right. So I have two different expressions. I'm going to get a common denominator here. So I'm just going to have a long chain of equal signs. So this, I'm going to get a common denominator, so it's going to be k times k plus 1 times 2k plus 1 over 6 plus 6 times k plus 1, 20 squared over 6. Okay, just getting a common denominator. Question?
Like before we said not to show your scratch work.
Right.
When as you're working your way down through this, is that you show
I'll show all of this, what I'm doing. Well, this isn't scratch work. I mean, what I meant by scratch work is you should know what it looks like at the end. You should know what this statement looks like for k plus 1. So this is not really, like I can't just say, I wouldn't just say, okay, this clearly equals end statement. I mean, that's not justified in my mind. I mean, there's a lot of little steps to go through. So I would just kind of, just using basic algebra though, I convert this to the right form. Okay, you don't want to do too many steps in one equal sign because somebody reading this should be able to logically see how you got from one step to the next. So from this to this, okay, I see they're getting a common denominator. Okay, and I'm going to add these two expressions. And usually, when you do this, I like to keep these equal signs kind of lined up. So I start with this stuff, equals this, equals this, equals this, and I keep it. You know, if I'm using try to keep those equal signs lined up. I'm just going to come over here, equals, so k times k plus 1 times 2k plus 1 plus 6 times k plus 1 pi squared all over 6. Okay, so I've just added these two expressions. Now, what you could do, I imagine you could try and multiply this all out or something, and it'd be kind of a mess if you try and multiply it all out and then collect by terms and then try to factor it. This is pretty much factored already. I just need to, if I think of these as two big groups, I notice that they both have a factor of k plus 1 in common. So what I'm going to do, I'm going to factor out a k plus 1 from both groups. Okay, so from this group, I'm left with k times 2k plus 1. Okay, I'm pulling this k plus 1 out front. From this group, I still have a factor of k plus 1, and I have a factor of 6. So it's going to look like this. Any questions about that? So I took this k plus 1, I factored this k plus 1 out of these two terms, pull it out front. And that's good, because that's what I need. Remember, like I would have my scratch work on the side, and I know I need a k plus 1 in the final numerator. All right, this stuff right here, I'm just going to multiply this out, and then I'm going to factor it. So k plus 1, this would be 2k squared plus k. This would be plus 6k plus 6. Equals k plus 1 times 2k squared plus 7k plus 6 all over 6. All right, so this is a trinomial that I can factor. It factors as, so now here's where, if I work from the back to the forwards, the next, I already wrote this last fraction right here. It's going to be k plus 1, it's going to be k plus 2 times 2k plus 3. So this is where, if you know the last fraction, if you work backwards, it would match up right here. But just to verify, if you went in the forward direction, k times 2k is 2k squared. I get plus 3k plus 4k would give me 7k, and 2 times 3 is 6. So this is the correct factorization for this. And we're almost there. My next line would be this equals k plus 1 times, instead of k plus 2, I'm going to write it as k plus 1 plus 1. Because remember, I have to make it look in the right form. And then my 2 times k plus 3, I'm going to write that as 2 times the quantity k plus 1 plus 1 all over 6. So what I've shown is that, assuming it's true for n equals k, I've just shown that the statement is also true for the next integer, k plus 1. The sum of 1 squared plus 2 squared plus 3 squared all the way up to k plus 1 squared equals this.
By induction, it's also true.
Right. So I'm not done. I really need to cap it off with a conclusion. Okay? So, therefore, by induction, we have 1 squared plus 2 squared, 3 squared, n squared equal to n times n plus 1 times 2n plus 1 over 6 for all natural numbers n. Okay. Any questions? So every proof by induction basically follows the same formula, right? You have your basis step, you show the statement is true for n equals 1. Then the inductive step, you assume the statement is true for n equals k, and show that enforces the statement to be true for n equals k plus 1. Then you write a conclusion. Therefore, by induction, it must be true for all natural numbers, all natural numbers. The statement is true for all natural numbers. Okay? The only real difference is, from statement to statement, there's a few little algebra, tricks or, a few different algebra little things we need to do. Here, when you have two fractions, it's gonna be about combining the two fractions, making it look the right way. But a big hint is you should know what the formula looks like for k plus 1. If you write that down and kind of work backwards, it might help you meet up in the middle and you have all your proof, all the statements for your proof. Okay, any questions about that? Okay, so how did number 10 go? I noticed that number 9 in the homework was very similar to number 10. So did that help you if you get stuck? Mm-hmm. So it said something like 3 divides, what was it, 5 to the 2n minus 1, right? So
you heard use powers and you set R5 to n equal to 3a plus 1.
Yeah, you can do it a couple different ways. But the way the book did it is, so if 3 divides, so you assume it's true for k. So if 3 divides 5 to the 2k minus 1, then I can write 5 to the 2k minus 1 equal to 3 times an integer. The book likes to do this. They like to move this to the other side and say, well, therefore 5 to the 2k equals 3a plus 1. Okay. So then when you soup this up by 1, okay. So here's the thing. If I replace n with k, I get that. If I replace n with k plus 1, I don't get that. If I replace n with k plus 1, I get this.
So you get 5 squared times 2.
Yeah, which is actually 5 to the 2k plus 2 if you want to write without parentheses. So that's something I might just common mistake. It's 2 times that integer, so 2 times the quantity k plus 1. So the statement is that's probably really the hardest part of this because it's the inductive step, and this was actually for n greater than or equal to 0. All right, so it's 3 divides 5 to the 2n minus 1. For n equals greater than or equal to 0. Is that what it was? Yeah. Okay, so 3 divides 5 to 2n minus 1 for n equals n greater than or 0. We use induction. So now you start with n equals 0. So what does the statement say? When n equals 0, 5 to the 2n minus 1 is 5 to the 0 minus 1. 1 minus 1 is 0.
And 3 divides 0.
And, and 3 divides 0. Okay, so it's true for n equals 1. So now, suppose 3 divides 5 to the 2k minus 1 for some integer. Actually, for some k greater than or equal to 0. Right. Then by definition of divide, we know that 5 to the 2k minus 1 looks like 3 times an integer, which equals 3a for some integer a. Okay, so you have to use this somehow. Now, what does the statement say for k plus 1? When n is k plus 1, it looks like this. 5 to the 2 times parentheses k plus 1. This is the quantity you have to work with we'll be done with this step if I can show that 3 divides this quantity. That's the next integer after k. All right?
Go ahead.
Any questions about that? This is what I have to show. I need to show this looks like 3 times an integer. Okay? All right, so this is what I'm talking about. You have to use your exponent rules here. This looks like 5 to the 2k plus 2 minus 1.
Which is 5 squared times 5.
Yeah, and then, yeah, you think of this, break this up, 5 to the power 2 times 5 to the power 2k. So this equals 5 squared times 5 to the 2k minus 1. So what the book did is, I think they replaced this with 3a plus 1, right? If 5 to the 2k would equal 3a plus 1.
Right here, we can also replace 5 to the 2k minus 1 with 3a.
No, because this doesn't have a factor of 25. So it's just this quantity right here. So this quantity, so I think if you want to do it that way, the book I think would actually write another line here. If 5 to the 2k minus 1 equals 3a, then 5 to the 2k equals 3a plus 1. You might want to put that in your proof here. But alternatively, I might write it like this. 5 to the 2k equals, sorry. We can do it this way. I'm gonna put a 5 to 2k minus 1, and then, but I just subtracted 25. 5 squared times minus 1. So I need to add 25. Anyway, it's like 25. You can do it that way. You guys probably didn't do it that way though, right?
Yeah, I like the
Some people did it the other way. Let me do it the way the book did. So it's up to you which way you want to do it. 5 to 2k equals 3a plus 1. Right? Alright. So I'm going to replace this 5 to 2k, 25 here. 5 to 2k is 3a plus 1. Okay? I replace 5 to 2k with 3a plus 1. Yeah. So what do you get here? You got this equals.
I just left that as 25 times 3.
Yeah, I mean, right. You're going to need this factor of 3. So it's 25 times 3a plus 25 minus 1. Oh, it's 24.
That's a factor of 3.
Do I need to write it like? Do you want me to write it like 25 minus 1? Just distribute it 25. This equals 3 times 25a plus 24, which is 3 times 8. I mean, I'm showing a lot of stuff here, but. All right, so that's the goal, right? I wanted to show that 5 to the power 2k, 2 times k plus 1 minus 1 looks like 3 times an integer. So I can conclude that 3 divides 5 to the 2 times k plus 1 minus 1. So I'm done with the inductive step. Then you conclude, you write a sentence by induction. Finish off. The same is true for all n, and I'm not on camera. Goodness. Post on there. Okay. So you show, you have this 5 to 2k plus 1 minus 1, and you have a chain of equations, and so you get 3 times an integer, therefore 3 divides this. Then you say by induction, 3 divides 5 to 2, n minus 1 for all n greater than equal to 0. Any questions about, this is number 10, right? Okay. You had 3 more proofs, but they were odd numbers, so you can see examples of proofs for those. Any questions about this example? So you should, oftentimes, you see, I had to go back and kind of add something in here because I needed to use it a little bit later just to justify, and also think about, what you need to show at the end, and you can work your way back to when you have these long chains of equations. Okay? But, make sure, even if you get stuck with this, with the algebra or something, at least show me that you know the steps. Like you could put the last sentence on there, therefore by induction the statement is true for all, and that's right. That just to get yourself some more partial credit if you get, just in case you get stuck on a little bit of the algebra. Okay. Let's take a 2-minute break, and then we'll come back and review the rest of the stuff for the test on 1 second.
I'm sorry, I think I'm going when you have that 5 squared times 5 and 2k minus 1 at the very top of the board on the right-hand side, you can't just pull out that 5 and 2k minus 1 because that's like subtracted and you have to do multiplication. If it was this, then you could replace that with 3a, but it's not. This 5 to the 2k has a factor of 0.5 on it, and this 1 does not have a factor of 0.5 on it. Yeah. So you'd have to do it. That's why you have to do this kind of trick right there. Okay. All right, no more questions for 2 minutes. No, I'm kidding. Maybe I have more questions about it. Write this down. 1, 2.
4 through 10. So remember back in chapter 4, we started talking about direct proof. We start off with definitions. So I think you probably know these definitions by heart by now anyway. Like, what does it mean for x to be even? X equals 2 times an integer. What is x? What if x is odd? X is 2 times an integer plus 1. So, just to remind you, you need to know your definitions. I'm not just gonna like make you write. I know we had a quiz where I actually made you write out the definitions, but you don't need to be able to write out the definition. You just need to be able to use them in proofs, right? Like if I said, prove that if x is odd, then x squared is odd. You'd have to know how to prove that. So no definitions for use in direct proofs in all of our proofs. Okay. Then we also did direct proof. Okay, and I think it's safe. Yeah, if P then Q, so or P implies Q. So I think you guys are good. I think the quizzes and so on were good from that stuff. And you've done that. You practice that so many more times, right? You assume P and then conclude with Q. Anybody, any questions about the direct proof? I think it's pretty clear. Things like this would be like, if x is even, then x squared is even, or something like that, right? So you'd say, okay, suppose x is even, then x equals 2 times an integer, then x squared equals 2, the quantity 2 times an integer squared, and just go back and look at examples we did. Any questions about that? I wasn't really going to do any proofs, but if you have any specific questions. And in chapter 5 was the contrapositive. Okay, so we're proving these conditional statements. If P, then Q. Well, we know that this is equivalent to not Q implies not P. So this is the contrapositive of P implies Q. So remember when this is a good idea. I'll probably tell you to prove it by contrapositive, but the reason why it's good is because if this is a negative statement, then when you take the contrapositive, the negation of a negative statement would be positive. So it's nice when you have negations to prove them by contrapositives. It's also nice if not Q is a simpler statement than P, because if you start with because the rest of the proof is you use direct proof after you assume not Q, then you prove directly not P. Sometimes it's easier to work with this statement than it is the original P statement. But we've seen several examples of that. Let me give you an example of this. Like, example. So, x is an integer. If x cubed minus 1 is even, then x is odd. You see why the contrapositive might be a better way to prove this than a direct proof? If you did this directly, you would start off saying, okay, therefore x cubed minus 1, or suppose x cubed minus 1 is even. Then x cubed minus 1 looks like 2 times an integer. Then what are you going to do? You're going to take cube roots of both sides of your equation to get to x? It's just going to be too messy. To try to, because the only thing if you have a statement about x cubed and you want a statement about x, you have to factor it somehow or use cube roots, and it doesn't work. So that's why it would be easier to assume a proof by contrapositive. Just to give the reader a heads up, right? You write contrapositive in parentheses, so they know where you're going. So if you tell the reader, hey, this heads up, this is proof by contrapositive, then it makes sense that you would say, suppose, what would you say?
X is not odd.
You could say X is not odd, right? And then, you know, more common, you know, the more you see these types of proofs, you might even just say X is even, okay? It's okay to say X is even, but literally you would say, suppose X is not odd. We know that every integer is either even or odd, so then you would say, so X is even. Right? And then, where are you going? You want to show that x cubed minus 1 is not even, which is the same thing x cubed minus 1 is odd. Right? So that's where you're going. Right? So, okay, so if x is even, then x equals 2a for some integer a, and x cubed minus 1 equals 2a cubed minus 1 equals 8a cubed minus 1. Where are we going? Trying to show that x cubed minus 1 is odd. We're close. Do you believe that it's odd? What do odd numbers look like?
2 times the number.
2 times the integer plus 1. Yeah, so, you know, this looks even. This stuff looks even, right? It's 8 times an integer. This is even. So there's a factor of 2 here. 2 times something. This is 2 times something minus 1. I mean, could I just write this as 2 times 4a cubed minus 1? Would you be satisfied that that's odd? Even though that's technically not.
Could you distribute a negative third and then 2 times negative 4?
Yeah, that's add 2 minus 2, technically, yeah. So, yeah, I mean, this is pretty close. I mean, we can. I think we've even shown that if the 2 times a minus 1 is odd, but technically that's not the definition. This does not look like 2 times an integer plus 1. So we want it to look like, yeah, like a plus 1 and a minus 1. Yeah, there you go. So this, if I do a plus 1 and a minus 1 to get my plus 1, this is equals minus 2, which is okay because I can factor it. I can kind of combine it with this stuff.
So we can place the minus 1 in the parentheses.
This one's a little bit. I mean, I don't know. I probably would be okay right here, just saying it. It's, okay, therefore this is odd. But just to follow the letter of the law here. So this equals 2 times 4a cubed minus 1 plus 1. So I'm just doing this trick, adding 1, subtracting 1. 2 times 4a cubed minus 2 plus 1. Seems to be a lot of work, right? So I factor out that 2, so it looks like 2 times 4a cubed minus 1 plus 1. Now it looks exactly like 2 times an integer plus 1. Thus, x cubed minus 1 is odd. And therefore, x cubed minus 1 is not even. That's the conclusion we wanted, right? I don't know. This last three equations. I didn't look at the proof beforehand, but so I'm just wanted to make it look exactly like 2 times an integer plus 1. That's technically our definition of something being odd. Okay. Any questions? But I'm just trying to demonstrate the contrapositive, right? The proof by contrapositive, you assume not Q, you conclude not P, therefore, the statement is true.
Something like the book for number 13 from last week's homework had like a point where it's like K times 20 or K minus 1, and one of those has to be even, the other odd.
Yeah. So if consecutive integers are one's even, one's odd, so you know that the product is even. Yeah. So we use that. Yeah. Okay. All right. So that's chapter 5. So I'm just again trying to demonstrate the technique of proof by contrapositive. And if you get stuck on proof by contrapositive, again, if you can show me you know how to start the proof by contrapositive, you know how to end it, I can give you credit. I can give you partial credit. Plus, it also helps you kind of go backward and then kind of work again in both directions. Okay. So try to, if you get stuck going forward, try to work from the back to the front. And that might maybe just what you need to kind of finish the proof. Chapter 6, proof by contradiction. So remember what we did with this chapter? We did famous proofs like square root of 2 is irrational. There's infinite many primes. Those are still, I think, just they take a lot of time. They don't really. I think they're just too difficult for the level of a test where you're testing. I mean, you guys got like 6 chapters of material. The technique is important. You understand the technique, right? Suppose you're trying to prove if P, then Q. Right? You're trying to prove a conditional statement by contradiction.
Negation.
Yeah. So, the way proof by contradiction works, you want to show a statement is true. So, for a contradiction, you assume the statement is false. Okay? So, for the sake of contradiction, you assume the negation, right? You assume the negation of P implies Q is true. But we know that the negation of P implies Q looks like P and not Q. Then assume P and not Q is true. And then you produce a contradiction. Somehow you get a contradiction.
Even a
right. If you get some like x is even and x is odd. Contradiction. Okay. So you assume this statement is true and show that produces a contradiction. Therefore, your original assumption was wrong. If this is wrong, then that means that P implies Q is true, which is what you want. So usually, once you get your contradiction, you need to stop the proof, and then it's clear. But you really have to tell people you're doing a proof by contradiction. Again, you either put contradiction in parentheses, or you say some phrase equivalent to this. For the sake of contradiction, assume P and not Q. Okay. So let me look at some statements, and really, once you get the statement, your original assumption down, it kind of a lot of the proofs kind of, in some sense, kind of wrote themselves. Like you had. So n is an integer. If n is odd, then n squared is odd. Proof by contradiction. I would say something like, suppose n is odd and n squared is even. That is P and not Q. I mean, you could even literally say, suppose n is odd and n squared is not odd. If you want to be literally assume P and not Q. But that's basically what you would start with for this type of proof technique. Then you work with this. So if n is odd, then you show that n equals 2 plus 2 times n plus 1. You square it. You'll see that it has to it's odd. The n squared is also odd. So you have n squared is even. But you just demonstrated that n squared is odd. That's a contradiction. And n equals 2a plus 1 for some integer a. Then n squared equals 2a plus 1, quantity squared, equals 4a squared plus 4a plus 1, which looks like 2 times 2a squared plus 2a plus 1. Then n squared is odd. So that's a contradiction. So if I said n squared is even. Any questions with that? You can prove a lot of different statements using a contradiction. It doesn't have to be a conditional statement. Like square root of 2 is irrational. That's not a conditional if-then statement. But you always start off assuming if you want to prove a statement is true by proof by contradiction, you assume it's false, and then show that leads to a contradiction. Therefore, the original statement must have been true. Okay. That is chapter 6. Any other questions from proof by contradiction? Chapter 6.
You can't use a proof by contradiction and use a counterexample, can you?
Well,
Like if you got to the point they're supposed to is odd.
no,
and
see, a counterexample does not prove a statement. A
Yeah.
counterexample disproves a statement.
disproves it, yeah.
Yeah. So one counterexample can disprove a whole statement. But just giving a really good example, that does not prove a statement.
So if you do proof by contradiction, but you don't end up with a contradiction,
That's wrong. It's like, you don't get a contradiction, and it's not proved by contradiction. All right. Any other questions about chapter 6? Because really, chapter 7. Oh, okay, yeah. So chapter 7 we haven't talked about yet. Chapter 7 is proving if and only if statements. And proving there exist statements. Your question? Lots of really short, easy proofs. So chapter 7. You have so the idea is P if and only if Q. So you have a if and only if statement. You can prove this using two proofs. You prove that P implies Q and show that Q implies P. So this statement is equivalent to P implies Q and Q implies P. Okay, they're not cases. They're, I remember when we were doing these homework problems, a lot of you wrote like case 1 this, case 2 this. If they're not cases, you have to prove two statements, this statement and prove this statement, then you can assume this statement. Very equivalent.
In case you just write forward arrow.
Yeah, you would just write, yeah. So like one paragraph, you can start off like, okay, this. And then you assume P and show Q. So, assume P, plus Q. And the reverse statement. Now you assume Q plus P. Now you're done. You've shown P implies Q, and you've shown Q implies P. You're done. Other ways to do it is you would actually write a phrase. You say, instead of showing this, you would say, first we show that P implies Q. Therefore, assume P. Then new paragraph. Conversely, we show that Q implies P. Now we assume Q is true. And then okay. This is a little bit, I think, a little bit shorter because I don't have any words, just have arrows. So that's basically, this is the outline of a if and only if proof. Any questions about if and only if proofs? Just remember, you really have two things to prove. Okay. And then each one of them is. Now here's another thing I want to point out. You can show my outlines here. I use direct proof to show P implies Q. Here I use a direct proof to show Q implies P. But you don't have to use direct proof. I think there are some homework problems where showing the reverse implication, it might have been easier by contradiction or contrapositive. Or you could use proof by contradiction. You can prove it any way you want, but you just need to you prove both of these statements. The proof of this might be direct. The proof of this might be contrapositive, or whatever technique you want. Okay, so keep that in mind too. Right? Because remember, one of these statements might be a whole lot easier to work with. I think we had a homework problem. Let me see. Chapter 7. I think it was. So x is odd if and only if 3x plus 6 is odd. So if you show this a forward implication, you would say assume x is odd, and you would show 3x plus 6 is odd. That's direct. But then you'll have to show that 3x plus 6 is odd implies x is odd. You might prove that by contrapositive. You would start off with saying, okay, let x be not odd. And then, so x is even. Then you would have to show that 3x plus 6 is not odd. So 3x plus 6 is even. So that's an example where proving the reverse implication might be easier by contrapositive. Okay, so you'd have, so both x is odd, but for the reverse, I might use contrapositive. So I might say, so the reverse implication is 3x plus 6 is odd implies x is odd. But by contrapositive, I would start with, suppose x is not odd. Okay. That's if and only if statement. Any questions about if and only if statements? Yes.
For the bottom one, you might have to use the 3x plus 6 to go the other way.
Yeah, to prove the 3x plus 6 is odd implies x is odd, I'm saying you could prove that by contrapositives. The contrapositive would be not this implies not this. It's kind of, it's kind of working backwards. I'm going backward and then flipping it again, and it's going to be going forwards. So this would be my, not Q here. Yeah, this is what we want to show, right? We want to show that 3x plus 6 is odd, implies x is odd. That's the statement we're trying to prove on this half, right? But if I want to prove this by contrapositive, I would start by assuming x is not odd and show that 3x plus 6 is not odd. Okay, any other questions? And the last thing, in chapter 7 was the there exists proofs. This just need to. It's kind of similar to find a counterexample, right? You have to show for there exist statements. All you have to do is produce one example that works. You remember that kind of stuff. Those are kind of sneaky, right? We did one, right? That there exists a natural number n such that 11 divides 2n minus 1. What was was it like 31 or something like that? Or what was it? It was like a high number, it seems like. 10? Oh, okay. I couldn't remember. So 2 to the power 10 minus 1 is divisible by 11. What we're saying? Yeah, so you just have to, say, so proof, you just say, let n equals whatever number that works. And then you got to show that it works. So n equals 10. Then 2 to the power of 10 minus 1 equals some number. I don't remember what it was. But you have to show it equals 11 times something, right? Some other number. So this is 1,023? Does that equal 11 times something? Okay. Thus, 11 divides 2 to 10 minus 1. It's kind of like a count example, right? You're just trying to find, and this isn't a count example because it doesn't disprove the statement. It's an example that shows the statement is true. There does exist a natural number n such that 11 divides 2 to the n minus 1. Any questions about that? And we already kind of reviewed chapter 8. I mean, that's the set stuff when we went over the quiz today. Just remember how to start your proof. Right? I wrote this the other day. If stuff, then A is a subset of B. Okay? You don't worry about this yet, right? When you're proving a subset, this is a subset of something else, you're going to use this stuff in your proof, but you don't need to start out there. You need to start with this relation. You need to take an arbitrary element of this set and show that it's in this set. How do you do that? Well, then that's where this stuff comes in. So your proof goes like this. Let x be an element of A. Then x is an element of B. Okay? And then here, the intermediate stuff, that's where you use all this stuff. Okay, that's the template. Okay? Don't start saying, well, x, assume x is here somewhere. That's not where you start with. You start with the relationship you're trying to prove. Whatever this set is, take an arbitrary element of this set, using all the other given information, show that that x must also be in here. And then you're done. You've shown that A is a subset of B. Okay? I give you one of the quizzes on that. Any questions about subsets. And then showing the two sets are equal, you could just show two of these proofs that show the left-hand side of the subset of the right-hand side, or the right-hand side of the subset of the left-hand side, or you show the equals, or if and only if statements. Chapter 9 was contradictions, chapter 10 was induction. I did 2 examples of that today. Any other questions? Did you guys already studied and had questions addressed
Just
from your studies?
feedback from.
Now, when you're studying, what you did, you did your homework and we went over that and stuff. So, I would just go back over proofs from class, proofs from homework, and quizzes. I'm sure you can do a proof of each type. Okay? I'm not going to try to invent new type of problems. I'm just going to plenty of stuff that just plenty of different techniques. I'm going to just give you a proof from each type. All right. Any more questions you think of?
The only definitions we're going to need to know are the ones that we actually done in this class.
Yeah, the ones we've done in the class. Yeah, and like, even, odd, divides.
Do we do parity?
Parity. I could potentially click on parity.
Because if you know even and odd.
Yeah, even odd, same parity, odd or opposite parity. I did do. Last time I had a quiz, I gave you the definition of rational and irrational. But not sure. You might need to know that too. Like I said, I haven't done the test yet, but just all the definitions we work with, some of them are like second nature probably by now, right? If I say x is even, I think it was 2 times an integer. It should be that quick. But just again, practice the techniques. And now we'll post today's review on